We were talking last day about networking. We need to talk a little bit more about networking. We're going to talk some. This course, I'm going to talk a little bit more in your 261 course, kind of from the other end of things. We said the International Organization, Standards Organization has a network model. It says kind of, you don't need to know this. And I said last time, kind of the reason, well, the reason you kind of don't need to know this is really TCP/IP has kind of overtaken all of this. And you'll see kind of where they map in a few minutes. Where they do, it is kind of nice to look at is if sometimes in a higher and gear, for instance, you'll hear of something like a layer 2 switch or a layer 3 switch. And so a layer 2 switch is talking about working at the data link layer, and that's a typical switch. We deal with everything in the one network. It deals with MAC addresses. And so I can't get beyond this network. There are some switches known as layer 3 switches, which can actually redirect things at the IP layer, at the next layer. And so knowing if they say layer 2 or layer 3, where they're kind of talking about things. So on this, physical layer 1 is all about, am I looking at either ones or zeros on a wire, maybe a differential signal, is it light on, light off in a fiber, or how am I actually getting things across the wire? It's not concerned with what the meaning of any of that is. It's just how did I actually get the signals, the bits from one place to another. So again, I either turned on or off a laser for on and off, or I had a positive or negative voltage maybe, or I had bursts of data transmission. So that's what you're concerned with on the layer 1. Don't know what it means. It's just ones and zeros going across the wire. When we go to layer 2, it's the data link layer. And we think of Ethernet on that. It's got a media access control or NIC address, hardware address you can hear about. And so it gets the ones and zeros that came from the physical layer, and then it packages them up into this data link layer, gets addressing out of that information. There's a checksum to see if the data was good. And then it may take that and put it up to another layer. And so we have layer 3, which is the IP layer. Now at layer 2, MAC address, and we talked about this, I have enough information to get something anywhere in my network. And if this is all the network, then you all have a MAC address, and I have a MAC address, and then I can ask, for instance, who is at a certain MAC address and send the packet of information, the data frame of information actually, over to whoever's sending. And there's a broadcast, and we can send out information. To go beyond this network, to get it somewhere else in the world, there's not enough information here. Because because data link layer is a 6-byte hardware NIC MAC address, but it's flat file. There's no hierarchy to it. So in order for me to know to send something anywhere in the world, I would have to know what everybody's MAC address is and keep it in some sort of memory or some sort of lookup table to be able to send it out. It doesn't scale very well. It worked fine in the local network, but we needed some kind of hierarchy, and that's where you have IP. And so IP, typically IP4 addressing, although IP6 has, I think, more IP addresses than there are grains of sand, for instance. But IP4 is a lot of, is still what's going between all the different networks. And with that, I have a hierarchy. So there are servers out in the world that know where different places are. And if my router does not know where the address is, it sends packets that are destined for not my network to somewhere else to other routers. And that router may go, oh, I know that if I'm sending it to 10 dot whatever, well, 10 dot is Australia. So I'll send it towards Australia, and a router in Australia will get it and go 10.52. Whatever, that's Queensland. It'll send it over towards Queensland. So there's a hierarchy to it. And so routers talk to other routers and they send the packets along. And one of the cool things about packets is that when they designed an IP packet, and we'll look a little bit more about how some of the components are of it, but one of the awesome things about packets was somebody put what time to live as one of the options. So every time your packet goes through a router, it deducts off the time to live. And that was very clever, because if I send to somebody and they're no longer there, that computer's no longer hooked up to the network, then eventually, as it goes through routers, it keeps deducting off the time to live. And when the time to live is less than what is set in the router doesn't forward it anymore, tosses it out. Okay. If you didn't have that, I could be sending something to, for instance, I'll send a packet to Wayne, and Wayne retired and went to live on a beach somewhere, and I don't want this thing traveling around trying to find Wayne and cluttering up the internet with thousands of packets that will never ever get to their destination. With the time to live, as soon as you've gone through a certain number of routers, it's toast. Okay, which is awesome. And I say normally you could take one off the time to live or however, but you as a router can decide that you're going to take a larger number off the time to live and not let it pass like through maybe your network. So network IP, the IP, it's hierarchical. It has enough in those 4 bytes to get our packet anywhere in the world. I could have you build up an IP packet at this layer and send the data to anywhere in the world. And it will traverse out of this network to our router, because it wasn't based on the network mask. Our system said, hey, it's not for here, it goes to the router. The router goes, I don't know, wherever that IP address is, passes it to other routers, and off it goes. Okay. But if the addressing is enough to get me anywhere in the world, then what's at the layer 4? That's where our TCP and UDP. What did this give me that layer 3 did not? I can get anywhere in the world with layer 3. What does layer 4 give me?
Got to check to see if it actually got there.
Yeah, well, TCP, for instance, would do, but what's at that other? Layer 3 gets me to the end node, a computer anywhere in the world. Layer 4 gets me to the application on the computer anywhere in the world. Okay, because what I have here are port numbers. So if I had a web server sitting there, chances are it's sitting at port 80. 1024 and below are all reserved. There are FTP is a certain port. The web servers typically are at port 80, although some are port 8080. If you don't want normally somebody to see your web page, maybe it's configuration for a router. It might be at a non-standard port number. But there's an application sitting on that computer running, listening at that address. And what you saw when we did TCP, you picked up server port address 7777 or what have you, and then we sent stuff using our Node MCU with the AT firmware, and we made a connection, and it picked a random port number above 1024, and then we sent it to the server. And so we had the server's IP that packet sender was sitting at port 7777, and then wherever I was on the same network here, I could send the data, and the TCP packet would make it all the way over to that packet sender, and the sending IP and its port number and the receiving IP address, which was the same, and 777, so the server was the same, that made a connection. Now, as long as the packet sender was you could have multiple node MCUs attached to the one packet sender, and it would keep everybody separate because they're individual sockets. Because the sender IP address is going to be different on each person, although I could have multiple packets sent from the same IP address. I could open up a few different instances, let's say, and be trying to send different things out. But the port number is randomly generated. IP is the same, port number is different. Receiver, same port number, same receiving address, but they make individual sockets. That's why if I download multiple files, they're not intermixing with each other. Each one is its own separate connection, okay? So its own socket. Layer 5, 6, and 7 are kind of merged in and gone away. It was session layer was kind of setting up individual connections. Presentation layer was more where that really mattered was things like I'm talking to an IBM server. IBM servers for a long time, I don't know what the current status is, talked EBCDIC as opposed to ASCII. So at that layer, you would do the translation. So if I'm sending you, because I'm a NEC computer and I'm sending to an IBM mini computer, for instance, then you would have to do that ASCII to EBCDIC translation. And then it would translate it back to ASCII when it's coming back. So that would be kind of at that layer. And then the application layer is any of the interface to your actual interface. And again, most of these, if you look at the 7 layers, then when we go down to the TCP/IP network, which is really kind of used, the link layer kind of incorporates the physical and layer 1 and layer 2 in the old one. And then we have the IP layer, and then we have the transport layer, which is where we have the TCP and UDP. So this is MAC address physical. This is IP. This is TCP, UDP. And then this kind of incorporates all of those last kind of layers there. Okay. And so it kind of shows us here the different ones. So you see layer 5, 6, and 7 are kind of the application layer. And the type of protocols you have there are HTTP, so hypertext transfer protocol, so web interfaces, simple mail transfer, POP3 version file transfer protocol, things like that. So those are applications, protocols that are sitting on top of either TCP or UDP, and those use IP, and those use either Ethernet, point-to-point, or something like that. One of the things looking at the down in the first layers, for instance, ARP, address resolution protocol, or reverse ARP. Anytime, for instance, I want to send something in the local network, I will say, hey, who's for instance, got IP 192.168.1.1, and I'll broadcast that out, and somebody will respond back and go, that's me, and send the MAC address. And then I will send data to you with that MAC address. Now, chances are if I sent one thing to you, I want to send something else to you. Well, it doesn't make sense for me to go just the very next frame, hey, who's got 192.168.1.1, broadcast out to everybody, and you go, yeah, that's me, and then I send you another frame. And then a frame later, I go, hey, who's got 192.168.1.1, and you go, yeah, that's me, and then I send. So you should have some kind of memory, okay? And so there is a cache to know where the IP related to the MAC address is for everybody. And so that's awesome. That means I say, come in and I say, I want to send some stuff to 192.168.1.1. So I broadcast out and I go 192.168.1.255, broadcast out to everybody. So everybody listens and say, who's got it? Somebody goes, that's me. And I send stuff to you. And now I remember it for a while. 5 minutes to 15 minutes, something like that. I don't want to keep it forever because you graduated and left 2 years ago, and now my ARP cache is full, and and I didn't have enough memory and all that, so I forget. And kind of the times again, 5 to 15 minutes, I'll forget. And then so if I send something to you and then I didn't send something in a while, I might have to go, hey, who's got? Okay, but if we're in a constant communication, it cuts down on the overall transmissions and things. So you have that kind of stuff. We will, that's on that page here, we'll continue on talking about it coming up next day. But basically, everything is looking at the layer below, sending data across, and then decoding things. And we'll talk more about it next day. We've got a couple of weeks of this, I think. Thank you.